We'll start with some question time. Do you guys have stuff that you want to talk about? 5-1 or 5-2 problems? Blake.
Would you mind doing number 48 on 5.2?
48. Sure. Let's. Okay. So it says if the integral from 1 to 5 of f of x dx is equal to 12, and the integral from 4 to 5 of f of x dx is equal to 3.6, find the integral from 1 to 4 f of x dx. So the tool I'm going to be using to do this is this property of integrals that we talked about last time. So if I piece this together, I can say that the integral from 1 to 4 f of x dx plus the integral from 4 to 5 f of x dx is equal to the integral from 1 to 5 f of x dx. So I can say that the integral from 1 to 4 f of x dx plus 3.6 is equal to 12. And if I just subtract the 3 point... Yeah. So do that, and what do we get? We get 8.4 or something. And we're done. Hi, Luke. You still owe me a calculator.
Yes, I was busy community tab. I'll bring it to you in class.
Okay. Oh, hold on. This is the wrong strimple. I have Robbie. This is for Thomas.
Oh, okay.
So I think they probably looked up the wrong kid to put the wrong room on there. Got your back, Robbie. No problem. All right. Blake, you feel okay with that?
I do, yeah.
Okay. So like way easier than you're probably trying to make it. But recognizing that like that was the property that you needed was maybe not super obvious straight from jump, right? Especially if it's like 10:30 and been doing this for an hour or whatever. Sometimes that, you don't see it. But that's again, this property is one that'll come up, is a nice one to use. And right here, we're just kind of using it to illustrate how you might use it. Mackenzie.
Can you do
Number 9?
Yes.
Sure. Let's go back and grab that. Okay. So I took the directions with this so that we can read those also. All right, it says use the midpoint rule with the given value of n to approximate the integral, and then round your answers to 4 decimal places. So first thing I'm going to recognize is that this is a trig function, so that when I go to do this, the mode for my calculator should be in radians. So right away, I recognize that this is a calculator or problem, and I should make sure my calculator is set up so when I come time to do it, I don't forget to do it then and end up like going, oh, that doesn't not right the answer. Okay, so our interval is from 0 to 8. So the delta x I'm going to be creating is going to be 8 minus 0 divided by 2. I'm sorry, divided by 4, which is 2. So my intervals are going to be 0 to 2, and then 2 to 4, and then 4 to 6, and then 6 to 8. So the midpoint in my first interval would be 1. The midpoint in my second interval would be 3. The midpoint in my third interval is 5. And the midpoint in my fourth interval is 7. So what I'm going to have here is just going to be delta x times f of 1 plus delta x times f of 3 plus delta x times f of 5 plus delta x times f of 7. So at this point, I'm just going to use my calculator. So I'm going to input my function, my f of x, which is sine of the square root of x. And then we're just going to do 2 times, and I'm just going to kind of compress things for the sake of not having to press the button a million times. So each of these are multiplied by 2, so I'm just going to do 2 times the quantity. I'll just do f of 1 plus f of 3 plus f of 5 plus f of 7 so I have 618 or how many decimal places? 4 decimal places. So this is about 61820. Does that feel okay, Mackenzie? Yeah. Sure, no problem. Anybody else? We can always come back and do more later too. Like, don't feel bad if it's like, yeah, I just haven't had a chance to really dig into this super deep and I haven't run into anything where I've had questions yet. That's okay. You know, we can always come back. Blake?
Do you mind doing number 42?
5.2, 42? Sure. Okay.
Wait, is this the same kind of thing as number 48? Like where you use that same property?
Not the same property there. Nope.
Okay.
The key that I'm going to notice is that if I look at the bounds have swapped, right? I went from 0 to 1 and now I'm going from 1 to 0.
Yes.
So that's the thing that I noticed, and I know I have a property to deal with that. Where did that one go? There it is. So the key here is going to be using is this property.
Okay.
So first and foremost, I know that the integral from 0 to 1 of 3x times x squared plus 4 is equal to the integral from 0 to 1 of 3u square root u squared plus 4, right? Oh, this should have a dx and this should have a du, right? Those are the same integral, have the same value, right? Because the name of the variable doesn't matter.
Yeah.
Everybody agree? Okay. So I know that this integral is negative of this integral. And that would be then 8 minus 5 root 5. And there we go.
Oh, okay. Yeah, I see it.
I think that's it. So again, I tried to pick these ones at the end. They're not, like, don't require a bunch of calculation. They're just like recognizing and using these properties. In particular, these ones that tend to get reused rather frequently. Oh, that's supposed to be a dx. It just was messy. That's the one you're talking about, right? And the other one's a du. It just was messy. My apologies. For sure, you can ask about my penmanship because I know it's not great. Okay. I'm excited to do 5-3 because I think, yes, Mackenzie.
Sorry, I just have a quick question.
No, go ahead.
Can you go back to 9?
Yeah.
So when you multiply
Huh?
when you're multiplying it by 2, is it the n? Oh wait, never mind. That was dumb.
That's the delta x is what I'm doing.
Okay.
Okay.
That's the right triple, sorry.
Oh, it was supposed to be Robbie, not Thomas. Okay. So Robbie, it is for you. It's just a computer thing. So they had the wrong name but the right room. That I found surprising. I would have for sure thought it would be the right name in the wrong room. Anyways, so Mackenzie, you're happy?
Yeah.
Okay. Again, I was going to say I'm excited to start to do 5-3 because I think this really makes life easier. So what we're going to be doing, section 5.3 is about the fundamental theorem of calculus. And the idea here for the fundamental theorem of calculus is we're just going to be creating a link between derivative calculus that we did in first semester and this idea of integral calculus that we've been developing here the last 2 lessons. So what we're going to do to kind of construct this theorem is we're going to start with a function where I'm going to define my function g of x equals the integral from a to x of f of t dt. So this is a function in terms of f of x, where x is the upper bound on my integral. So what you can think about this as like the area so far function. So as x is changing, we're getting more and more of the area under our curve is increasing, right? Or it could potentially be decreasing if, like, my f of x did this or something, right? Everybody's okay with that idea? So the t is like a parameter, like a lurking variable. It's not actually part of our function g of x. Is everybody okay with that? So if I wanted g of like a plus 1, it would be like that area, right? Does everybody feel okay with the notation there? Okay. So just to kind of get comfortable with this notation, we're just going to do a little example. So say we have the function f that's in the picture there below. And we have the function g of x that's defined as the integral from 0 to x of f of t dt. And we're just going to evaluate the values for g of 0, g of 1, g of 2, g of 3, g of 4, g of 5. And then we're going to sketch a graph of what the function of g of x looks like based on those points. So if I wanted to do g of 0, if I'm plugging 0 in for x, I have the integral from 0 to 0 of f of t dt. And if you remember from last chapter, or last section, we had, that was a property, right? If the upper and lower bound is the same, the value of that integral is always going to be 0, because essentially you're calculating area whose base is 0. If I'm going for g equals 1, I'm talking about that region. Well, hey, that's just like a triangle, right? So I'll just do that geometrically. So the base there is 1, and the height there is 2. So 1/2 base times height is just 1. G of 2 is like that area, right? So if I do that, that's the integral from 0 to 1, which we just did, and then the integral from 1 to 2. Well, that area is just a rectangle, right? The base is 1, and the height is 2. So we have 1 plus 2, or 3. So far, so good? Okay. If I want to do g of 3, I'm talking about this area. So again, I'm going to have my answer for g of 2 plus this new part here. And I notice that this area is curved. So I'm not going to be able to calculate this geometrically. I'm not given a specific definition for my function for f. So what I'm going to do is just kind of make an approximation. So this one box is like 1 unit of area, correct? So that box looks like 0.9 of a box. You guys buy that? Sure. And this one up here looks like about 0.4 of a box. You guys buy that? A little less than half. So the area is just going to be 1.3 for that part. So if I take my previous answer for g of 2 and I add the 1.3 to it, I have 4.3. So far, so good. And if you're given a picture where it's like all gridded out, you can certainly calculate areas just by like counting boxes, right? Or approximate areas by approximating the area in a box and just adding those up. Is everybody okay with that idea? Very simple, right? Like nothing complicated. If I look at g of 4, I'm talking about this area. Now I notice that I have areas above the curve, above the x-axis and below the x-axis. So I know the part down here that's below needs to be a negative area. But if I look at this, this looks like basically the same shape as that piece was, right? So again, I would estimate that as like negative 0.9, and this one is like negative 0.4. So if I take my previous answer, which was 4.3, and I subtract the 1.3 on it, I get 3. Mackenzie? Yeah, that was our answer for G of 3, right? So that's the blue. Notice that in each of these calculations, I'm using my previous answer and then either adding or subtracting from it, right? For the new segment. So if I do g of 5, then I have another or some more area below. So I remember up to here, that was 3. That's my g of 4. And then this area, again, I can just approximate it. Looks like that same negative 1.3. So 3 minus 1.3 is 1.7. Is everybody okay with kind of what we're doing? It's just like this g of x function is like the area so far, right? The area up to that value of x. Does that feel okay? So let's go ahead and sketch a graph of what g of x is going to look like. So the x coordinates for g are going to be 1, 2, 3, 4, 5. And the y coordinates are going to be 1, 3, 4.3, 3, 1.7. So where did I do that? There it is. So there's my function for g of x, the graph of it. Everybody's okay with this? And what I want to do is I want to look at what the derivative of g is going to look like. And what does that mean in relationship to f? To f. Remember that, again, we described g of x as that function, right? Yeah, so g prime is kind of like the rate of change of its area. Sure. Yep. So let's look at that. So I'm going to take some value of x, because I know that like g prime of x is going to be the limit as h approaches 0 of g of x plus h minus g of x over h. Everybody agree with that? That's just our definition of a derivative. And here I've drawn we have a picture here to illustrate. So the height of my rectangle is f of x, and the width of that rectangle then is h. Everybody's okay? And we're looking at the rate in which that rectangle is changing size. So if I look at g of x plus h minus g of x, that is this rectangle, correct? So I can replace that with h of f of x. Or h times f of x, excuse me. And the h's cancel out. So f of x is a constant with respect to our limit. These are limits in terms of h. So the limit of a constant is just the constant. So this just all simplifies down to f of x.
Show this step between going from g of x plus h minus gx to h of x.
Yeah, it's this rectangle is g of x plus h minus g of x, right? So like g of x plus h is that area.
Oh, yeah.
And then we're subtracting off from it,
Yeah.
like this area.
Okay.
So you're left with just that blue rectangle.
I got you.
Is that,
Yeah.
you see it now?
Yeah.
All right. This is the payoff right here. What is this saying? So if I do like d dx of g of x, that's g prime, right? So that's going to be the same thing as d dx, the integral from 0 to x of f of t dt, which is, we know, f of x, right? What just happened here? Oops. Yeah. What just happened there? The derivative canceled out the integral. Integrals and derivatives are inverse operations of each other. This is great news for us. This is great news. That will make life enormously easier because we're already very good at dealing with derivatives. Right? Okay. So this thing now will formalize as the fundamental theorem of calculus part 1. And basically the idea here is that derivatives and integrals cancel each other out. So if I do the integral of d dx f of x dx, I should just get f of x. Or if I do the derivative of the integral of f of x dx, I just get f of x. That's the takeaway. Is that if I want to recover my antiderivative, if I have the derivative and I want to recover the original function, that's the same thing as taking the integral. If I want to, if I have an integral and I want to recover the actual function that we integrated, I take the derivative. That these two things just kind of operate as inverses of each other. Okay. So let's do a little practice now, because this can be a little bit more challenging. So if I look at this, find the derivative of g of x equal the integral from 0 to x of the square root of 1 plus t squared dt. What's that? Yep. Square root of 1 plus x squared. Okay. Blake.
I feel like I'm missing something.
Okay.
Like, so this fundamental theory that we're like starting to work with,
Mm-hmm.
but it can't work with everything, can it?
Mm-hmm.
Like, because I guess the way that I'm thinking about it is that like you take like the
Well,
integral of like a sine.
Got to be continuous and differentiable. Your function has to be continuous and differentiable over the interval that you're integrating on. So not everything, but sine is continuous and differentiable.
But wouldn't its integral just be 0 because it's oscillating over the
Its definite integral is 0, but that's not what g of x is. G of x is not a definite integral. It's a function where the upper bound of the integral is varying.
Okay.
So it's not, yes, the derivative of like the integral from a to b of f of x dx is 0. It's always going to be 0 because you're just differentiating a constant.
Yeah.
For sure. But that's not what we're doing here. We've defined this integral as a function of x.
Okay.
Where x is the upper bound of the integral. So it's not just a constant that we're differentiating. But you're right.
Okay. Yeah, I see what you're saying.
That's the piece that wasn't clicking in.
Yeah.
Okay. Let's look at this next one. What's the problem here with this? That is x to the 4th. So really what we have here is g of x to the fourth is equal to like 1 over x, or one integral from 1 to x secant t dt. So I went ahead and rewrote it as a composition.
Can you drop the x to the fourth on the integral?
Well, that's what I mean, if I wrote it this way,
Oh, okay.
right? That means that, we should say this. So g of x to the fourth is equal to this. Right? There you go. That's probably the clearer way to write it. If I take the derivative of this, what am I going to have to do? Going back to like chapter 3. If I have the one function inside of another function and I want to take the derivative, that's a chain rule problem. So if I do g prime of x to the fourth, I'm also going to have the derivative of x to the fourth stuck on at the end, correct? Okay. So g prime of x is just going to be secant x, right? So g prime of x to the fourth is going to be secant x to the fourth, and the derivative of x to the fourth is 4x cubed. So that's our friend. Everybody okay with how we did that? So again, the takeaway is when I have a function as the upper bound for my integral, if I'm doing a derivative, it's a chain rule problem. Got to make sure I'm doing a chain rule. Is that, we see it? Now here's the big payoff. Fundamental theorem of calculus part 2. If f is continuous on the closed interval from a to b, then the integral from a to b, the definite integral, the thing that we've been calculating and have been pulling our hair out trying to calculate, of f of x dx is cap f of b minus cap f of a, where f is any antiderivative of f. Wait, what? So this is saying to calculate an antiderivative, or to calculate this integral from a to b, this definite integral, all I need to do is figure out the antiderivative of the function and then plug in b to that antiderivative and subtract it from a plugged into the antiderivative. And I'm done. No more limits, no more sums, just going to use the antiderivative. So remember this guy that we did yesterday that was like a half a page? Look at the space that I've provided for to do it here. Okay. So what is the antiderivative of e to the x? E to the x, right? And then I just need to evaluate that at x equals 1 and x equals 3. So that's the notation we usually use. So e to the third minus e to the first, which is exactly what we got after like a half a page yesterday. Look at what we just did. Yes. So because it's any antiderivative, we can pick the c to be 0. Since it's any antiderivative, we'll just pick c to be 0, which is awesome, right? Like, how easy does this make this? Makes it massively, massively easier. Let's do another one. So we want to find the area under the parabola y equals x squared from 0 to 1. So we need to do this, right? Okay. What's the antiderivative of x squared? Right? X cubed over 3. And we'll evaluate that from 0 to 1. So 1 cubed over 3 minus 0 cubed over 3 is equal to 1/3. And we're done. This was a problem that we did in section in 5.2 also, or maybe 5.1 even, but it took like a half a sheet. It was a half a sheet problem. Look what we did. We did in like one line. Mr. Kulik, I like where this is heading. All right. Let's look at this one. So we have the integral from 3 to 6 of dx over x. How do we want to be thinking about this? 1 over x times dx, right? What's the antiderivative of 1 over x? Yeah, that is a natural log, right? But it's the natural log of the absolute value x, right? That's the antiderivative. And then going from 3 to 6, we have natural log 6 minus natural log 3. Or if you wanted to, you could use your logarithm properties to rewrite this as not ln, yeah, divided it. So this just could turn into ln2. Who's excited about how this is going? Mia. So that's just the antiderivative rule. If you went back to 4.10 or whatever, or 4.9 when we did these, let me just grab it. So I'm just pulling the thing. The reason is that 1 over -2, you can do. The natural log of -2, you can't, because you can't take you can't take any logarithm of a non-positive. So 0 and negatives are no dice, no bueno. So that's kind of why that ends up in the net, or the absolute value ends up in there. I'm just going to get rid of that because I didn't leave myself enough space when I inserted it. Okay. Let's do the area under the cosine curve from 0 to b, where b goes from 0 to pi over 2. So there's that, right? What's the antiderivative of cosine? Close. Negative sign, I believe, right? Oh, no. No, it's positive. It's positive. It's positive. So sine of pi over 2 minus sine of 0. What's sine of pi over 2? 1, and the sine of 0 is? So we just get 1 as our answer. Anybody know a summation formula for involving a sine? I sure don't, but this I can do in like a minute. Thanks. Blake, it's for you. All right. So again, to summarize what we've done here today, fundamental theorem of calculus. If f is continuous on AB, then integrals cancel out the derivative. That's part one. Part two, the integral from a to b of f of x dx is the antiderivative evaluated at b minus the antiderivative evaluated at a. That's the takeaway. Did this just get a whole lot simpler? Yeah. Now, from where you sit, we can only do simple antiderivatives right now. We'll address that in sections, in section 5.5. We'll come up with a technique to deal with, like, if I did, if I wanted to do this, the antiderivative of that is not obvious. Right? We'll see how to deal with something like that in section 5.5. And there's still other antiderivatives that'll be difficult or not realistic to do. There's a variety of other techniques to address those sort of situations that we may see, depending on time permitting, are not necessarily A-B topics, but are good things to do, particularly if you're going to take a Calc 2 course at some point, which probably a lot of us in this room have notions of doing. So that's it for today. I feel like that's enough, right? You guys feel good? This is nice? Yeah, it is nice. We'll stop.